Hello, everybody. This is Miss Peachy from WCA Physics class, and today I'm just kind of doing an overview of a couple of different lessons here, just as preparation for your upcoming unit test. So this unit is on energy and work, as we've seen before, and a few of these lessons now towards the tail end of the unit start dealing with conservation of energy and the work energy theorem, which is kind of what we're going to be discussing here in this video recording. So I'm not going to go slide by slide through each of these lessons, but more so want to kind of focus on some general overviews and overlying principles. So just as a reminder of some of the things that we already know. Okay, so we know that kinetic energy is 1/2 mv squared. That's a known. We know that potential energy is mass times gravity times height, or mgh, mass times gravitational acceleration times height, and that potential energy, elastic potential energy, is given as 1/2 kx squared, where k is the spring constant, excuse me, and x is the amount of displacement of that spring. So we can use that to determine potential energy of the spring. So that's something we can do as well. When we look at any system, we know that energy is conserved, mechanical energy is conserved, and because of that, potential energy plus kinetic energy will be equal to the sum of all the energy. The total energy is equal to kinetic plus potential. So we need to look at and kind of break down both of them within the system, and that will help us to understand different components of that system as well. So that's kind of what we're starting off by looking at here, conservation of mechanical energy. In this lesson, they're going to talk specifically about a pendulum and looking at, how to determine what factors are affecting the period of the pendulum. I don't want to go into detail on that one, so I'm going to go ahead and go to lesson 6, which is energy and work apply. So as soon as this one loads here, we can see kind of what we already know. And so what I was just talking about a moment ago is this total energy. Total energy is potential energy plus kinetic energy, and it remains constant so long as no friction is present. So from our examples we will be doing, we'll be looking kind of at systems in which friction is absent. So frictionless systems. These are fictitious systems. In reality, friction's always going to be there. But just to simplify things, we look at systems where friction is not present at all. That helps us to better understand things. So this is actually the problem that is given here in the slide. I'm just going to go ahead and erase this information here. So in this lesson, we get this particular example problem, which is going to help you to get prepared for your unit test. Now, in class on Friday in our live lesson, we are actually going to be going through this problem step by step. So if you come to virtual class, come to live lesson on Friday, then we'll go through all the components of this problem. I don't want to do that right now because that's something we're going to be going through in class on Friday. I was just kind of giving us a little blank piece of paper here because otherwise I don't have any place to write. So we have our total energy. I like to write it as, and sometimes you'll see it written as, the sum of all energies, right, is equal to potential energy plus kinetic energy. And I'm writing this a little bit different. Instead of putting GPE as gravitational potential energy, I just put potential energy with a little subscript of G that indicates it is a gravitational potential energy. Both of those denotations are acceptable. And so the idea behind this is that these energies can be added together and they can help you determine different parts of what is going on in the entire kind of scenario. So for example, just to give a slightly different example, let's say we had a skier that was skiing down a slope and there was a jump on the slope and then the slope continued down, right? So we're going to draw our picture of our skier up here. They're skiing. and they're going down, and we would know some information about this. There we go. And not the most prettiest picture, but that's okay. Let's say we knew the mass of our skier and we knew the height of the hill. So our skier, I'm doing a little mental math here. Let's say is around, I don't know, 60, let's say 70 kilograms. Let's make us all feel better. It's 70 kilograms. That's still pretty light, actually, but 70 kilograms is the mass of our skier. And the height of our hill here, we're going to put as 100 meters. Okay. So just knowing this minimum amount of information, we should be able to answer the questions, a few questions. One, what is the speed of the skier at the bottom of the hill? You might think like, how in the heck could I possibly get that information? But I'll show you that in a minute. You could also get the speed of the skier pretty much at any point. We can make a point right here. We'll call this point A, and we'll call this point B. I should be able to determine the velocity of my skier at any one point along the track using the equation for total energy and also knowing just a couple pieces of information, the height of the hill and the mass of the skier. So let's first start off with what is the total energy in the system? So at the point where the skier is right up here at the top of the hill, right here, right? That skier has 100% of their energy is potential, gravitational potential energy, and 0% is kinetic energy. So at just this point and no other point along the track, I'll make this a different color. Just here, at this point here, the sum of the energy or total energy is going to be equal to potential energy at that point, okay? Because again, kinetic energy is 0. So all their energy is just potential. So kinetic energy is 0. All the energy is just potential. Well, I can easily figure out potential energy because our formula for potential energy is equal to mass times gravitational acceleration times height, right? And I know those variables, all three of them. Gravitational acceleration is always 9.8 meters per second squared. We know the mass and we know the height. So let's go ahead. I'm just going to get rid of this for now, just to get it out of the way. And we'll put our mass of our skier down here just so that we have more space. I'm going to go ahead and calculate potential energy. 70 times 9.8 times 100. I'm not including the units just to make the writing a little bit easier, but it is always good practice when you're doing these calculations to include your units because it does help you avoid errors in calculations, making sure that your units are canceling and so on and so forth. I advise you to do that. It's really difficult for me to put all that information on my screen just because my writing utensils are really, really fat and I don't have much space, but that's something I would certainly advise you to do. So let's go ahead and multiply that out. Calculator right here. 70 times 9.8 times 100. That tells us the total energy of our skier here. So that, remember that potential energy at this point is equal to total energy. And that's just here. We'll call this point number 1. Okay. So this number is 68,600. And so we know that is equal to our total energy. That's really, really important to determine the total energy. And so that's the first step you're always going to have to do is to determine the total energy at the point where they're at like their maximum height. And at that point, all of the energy is in the form of potential. Okay, so now that we know the total energy, then we can determine the kinetic energy at any spot. You might wonder, how would I do that? Well, remember that total energy is equal to potential energy plus kinetic energy, right? I can determine the potential energy at any spot just by knowing the height. I do need to know the height. So the height here at A, we're going to say is 60 meters. So if I know the height of spot A, I can determine the potential energy. I also know total energy. So let's fill in the knowns at this point. So if I want to determine the velocity at point A, I know that total energy is 68,600 joules, by the way. I know potential energy is mass times gravity times height. So that's 70 times 9.8 times 60. I know that the mass of the skier is 70, so 1/2 times 70 times v squared. So the only thing at this point that I do not know is the velocity of the skier. That's the only unknown that I have in this equation. I'm going to go ahead and make this bigger so I have a little bit more space to work with, okay? So let's go ahead and solve this problem here then. So we have all the information, our knowns, remember, except for v squared. So let's go ahead. That's 70 times 9.8 times 60. So the potential energy at point A is 41,160. Okay, so my next step is 1/2 of 70 is 35, right? So I'm going to subtract 41,160 from both sides so that I can get rid of it. That gives me 27,440 equals 35v squared. Now I'm going to divide both sides by 35 to get rid of the 35 on the right. This cancels. Gives me 784. And now I just need to take the square root of both sides. So it tells me that the square root of 784 is 28. So V would be 28 meters per second. So the velocity at point A is 28 meters per second. And you can apply this principle at any point along the track. You just need to know the height of the starting position, and they need to be starting from rest. And as long as you know the height and then the mass of the skier, you can determine the total energy, which is also equal to the potential energy at that point. Once you have total energy, you can calculate the potential energy at any point along the track. You can calculate the kinetic energy at any point along the track as well, right? Because you still have, because we know this, total energy equals potential energy plus kinetic energy. So if at this point my total energy was 68,600, my potential energy was 41,160, it would be easy for me to solve for kinetic energy by just taking that 68,600 and subtracting 41,160, right? So we can do that very simply. And then we can also, once we determine what the kinetic energy is, which happens to be this number here, we can then use that 1/2 mv squared to solve for it. And so that's essentially the skill that you need to have for this unit test. If you can apply this information to different problems, then you'll do really, really well. So if you have questions on that, let me know. Like I said, we'll be going through the example that's given in the lesson review on Friday's live lesson. Otherwise, thanks for watching. Have a great day, and we'll see you guys in the next one.